So I mentioned some differences in reactivity among these carbonyl compounds. So let me lay it all out. These are all the functional groups that we've learned about that have a carbon-oxygen double bond, or if nitrile, are like something with a carbon-oxygen double bond. So acyl chlorides and hydrides, aldehydes, ketones, esters, carboxylic acids, nitriles, amides, and carboxylate ions. This is the order in which they are electrophilic, which is to say how reactive they are with nucleophiles. The most reactive of all these is the acid chloride, right? This is a great leaving group, and it's pretty electronegative, so it makes that carbon pretty electropositive. So when we talk about reactivity, really there's two kind of main things that we're looking for. We're looking for sterics and electronics. Sterics essentially is how crowded is it, and electronics thinks about, okay, is it electron rich or is it electron poor? So here, this carbon isn't very crowded and it's very electron poor, okay, because it's got this withdrawing group next to it. Anhydrides are about as reactive as acid chlorides. Next come aldehydes. So aldehyde, the hydrogen isn't exactly a withdrawing group here, but it's really sterically open, right? So this is not protected at all by sterics. So aldehydes are very reactive. Ketones have a little bit more shielding from whatever these R groups are. And so ketones are a little bit less reactive than aldehydes for the most part. Esters, we mentioned, are less reactive than ketones. That's mostly due to these lone pairs on oxygen helping this carbon be a little bit less positive. Carboxylic acids and esters, as long as this is protonated, there's really no difference in electrophilicity between this ester and this carboxylic acid. Nitriles are a little bit less reactive than carboxylic acids. Amides are even less reactive. We talked about how important this resonance between this lone pair and this carbonyl are. So amides are really, we mentioned that to, for instance, hydrolyze an amide, you need to kind of have boiling acid or boiling base, right? Because amides are really stable. And finally, carboxylate ions. If I've got an O minus, it's going to be really hard for me to get something else minus in there, right? So electronics more or less prevents this from being a good electrophile. Okay, so what are some ways we can use kind of this ordering? Well, one, we talked about sodium borohydride versus lithium aluminum hydride. And I said that sodium borohydride is less reactive. Here is your sodium borohydride line. So ketones, aldehydes, acyl chlorides, and hydrides, any of those will be reduced by sodium borohydride. Sodium borohydride will probably actually reduce these twice all the way down to the alcohol. But sodium borohydride often won't touch esters, nitriles, and amides. For those, you'd need lithium aluminum hydride. So lithium aluminum hydride will reduce all of these functional groups down. So lithium aluminum hydride will reduce all of these things down. It will even react with carboxylate ion if we have enough of it, amides, nitriles. It will react with all of them. However, it won't give us alcohols from all of these things. So how do carboxylic acids get reduced by lithium aluminum hydride? Well, like I said, anything even remotely acidic is going to react with hydride first in a very quick acid-base reaction. You'll see a lot of H2 hydrogen gas bubbling up, and you'll get this carboxylate. But even this carboxylate will get reduced by lithium aluminum hydride to something that looks like this. Okay, so this is O2 minus, and so here it seems like we're stuck, right? Like, am I going to have an H leaving group and O minus leaving group? No, what's going to happen is it's going to react with some of the AlH3 that got left behind from my reducing agent. So we'll get some intermediate that looks like this. Maybe I've got aluminum on both of those oxygens. But once I have this, now I could actually have this leave just like that. The aluminum is electropositive enough to help carry some of that charge away. And so this, it's a little bit weird to draw the arrows for, but this is how this gets reduced down to an aldehyde, which is obviously way more reactive than the carboxylic acid. And so you'll end up with the primary alcohol. So carboxylic acids first deprotonated, but as long as you have an excess of lithium aluminum hydride, it will first get deprotonated and then react twice more to give you the primary alcohol. How are amides reduced by lithium aluminum hydride? As you've noticed, I haven't erased all of that last drawing. I more or less swapped out an N-methyl for O. So here we would call this a secondary amide because it has an NH. Primary amide would have NH2. That verbiage isn't super necessary. But this works with primary, secondary, tertiary. It doesn't really matter if there's an NH on there or not. This still works. If there is an NH, though, the first step will, again, be deprotonation with this very strong base. Lithium aluminum hydride is a very strong base. So I'll get this N-, which is still reactive enough to react with another equivalent of hydride. I'll get this intermediate. Oxygen will, again, complex to aluminum, and then will end up being a leaving group. And so now, instead of an aldehyde, I end up with this compound that has a CN double bond. We haven't seen that before, I don't think. This is called an imine. Sometimes people, especially old-fashioned people or biologists, call it a Schiff base. These are really, really important in biosynthesis. Pyridoxal pathways, transaminase enzymes use imine intermediates a lot. Anyways, so from the amide, we're reducing that to this imine. But as you can guess, this is going to be really, really reactive. This is about as reactive as an aldehyde, if not more so. And so this is going to react again with lithium aluminum hydride very quickly to give us a primary amine. Not primary, but an amine. So lithium aluminum hydride reduces most CO double bond looking things, esters, ketones, aldehydes, reduces most of those to alcohols. But in an amide case, it actually doesn't reduce it to the alcohol. It reduces it all the way down to an amine, reduces it to an amine via an imine. That's good to know. Also, and I won't belabor this, but this is another way to reduce nitriles. We talked about using hydrogenation to do this with palladium on carbon, but lithium aluminum hydride will also reduce nitriles all the way down to amines. You can essentially picture it, I won't draw it out, but you can picture two equivalents of hydride adding one after the other, and then protonation gives you the amine. So amides, nitriles give you amines with treatment with lithium aluminum hydride. Most of our other carbonyl compounds give us alcohols. One last note about nitriles. We now know two different ways to reduce nitriles to primary amines. Lithium aluminum hydride will do it, so will hydrogenation with a palladium catalyst. We also know that we can hydrolyze nitriles under acid conditions or basic conditions to get to carboxylic acids. So it's two different things we can do with nitriles. And actually, if you remember, we learned that that reaction goes through amides. So we can get to an amide, or we can push it through the amide all the way to the carboxylic acid. So now these are three functional groups we can get to from the nitrile. And I'm about to give you one more cool reaction that nitriles can do. We talked about what happens when this reacts with this irreversible nucleophile. But what about the Grignard reagent? Let's make this phenyl magnesium bromide. pH is for phenyl. Okay, so again, what part of this is the electrophile? The carbon is the electrophile. This is my nucleophile. So my arrow is going to go onto carbon. this anion is actually stable in solution. I am not going to have another equivalent of Grignard reagent attack here, which is a little bit surprising to me, but it is stable. And so what will this do? This will stick around until we add some acid to it, right? We talked about the Grignard reaction before. We add acid to work it up to get the alcohol. If you add acid to this, the first thing that you form is that functional group that we just learned about, the imine. In water, this is really quickly going to react with that, you essentially lose ammonia. You trade out water for ammonia, and you'll end up with a ketone. All right, we'll talk about this mechanism in a few, probably if not the next video, then a couple of videos from now. So this ketone actually is my final product. I don't have this add twice like it does to esters, because at this step I'm adding acid, which not only protonates my iminoyl, whatever you call it, not only protonates this N-, but it also kills any Grignard I have in the pot, right? Remember, these things are really, really basic. You add an acid, boom, no more. So we don't have overreaction of nitriles. We actually end up with a ketone directly from a nitrile. That's a pretty cool thing to be able to do. And again, why do I think it's cool? Because I made a new carbon-carbon bond, y'all. Carbon-carbon bonds. They're literally what we are made of to a very, very large degree. Okay? So, nitriles. We can hydrolyze them to amides and acids. We can reduce them to amines by a couple different ways. And we can add an alkyl group to that carbon to make a ketone. Awesome.